Good morning, everybody, and welcome to Astronomy 120. Today is October 24th, and we are dealing with week 8. There are interesting topics that are going to be discussed today. Unit 25, which is not part of exam 2, not part of midterm 2, and that is actually part of midterm 3. So it's still a long time before we come to that midterm. The review for this midterm is posted and should be available for you guys, and you will have more than 2 weeks to actually prepare for the actual midterm. Midterm 2 is going to be October 9th. I'm sorry, not October, and we're done with October practically. Okay, it's going to be November 9th. That's a Wednesday of in about 2 weeks from this coming Wednesday. So this Wednesday is the 26th. Then the Wednesday after that is going to be November 2nd. And then the third Wednesday, if you wish, from this Wednesday is going to be November 9th when our midterm is. So midterm 2 is going to cover all of the topics we covered from from the previous exam, from the previous midterm. So it's an isolated midterm by itself. Basically, it's not comprehensive or anything like that. The review actually is online. So let me share with you basically this week so that you guys see exactly what's going on. There are a lot of things happening this week. So I really want you guys to pay attention to these things. Before I share that, let me remind you of a message I sent this morning, and you have received a different message from the college. There is an important survey that your input is valuable and is very important that you please go and fill it out. You have about 2, maybe more than 2 weeks, probably 4 weeks to take care of it. It's due November 16th. And that is again to basically give your input and how things are going so that we make things better. Okay. And if things you like and you think that needs to continue, also emphasize that so that we build on those things. Okay. So it's not necessarily everything negative. Whatever you think is positive also has to be included. So this is basically part of the process, and I really want to appreciate your help for that. And so let me share with you the content. Share this week. So we are at week 8. Again, the objectives are all the units that are discussed, namely 48, 49, 21, and 22. So again, these are the units that are covered this week. Wait a minute. Yes, these are the units. So the unit 25 is still incoming from next week, okay? So we still have to cover these units. It's still unit 25 is not part of this review, but you have the review anyway, and the review is for this entire exam. So please open it at your earliest convenience to start doing the review. Don't forget you have a lot of assignments from even the weeks before, okay? So you have the discussions from before, and you have other assignments from there. Now, this week you have several assignments that are coming at the same time. In addition to the review, which is a graded assignment, by the way, meaning you'll get points for doing it and you will get nothing for not doing it. How much you're going to get if you're going to start the review? You're going to get the full mark, which is 113 points, regardless of your actual score in it, because the intent is this is actually to help you prepare for the actual midterm. So and to encourage you to do that, you're going to get points for doing that. That goes toward your participation, the fact that you're doing what you need to do to pass the class. So again, this is graded assignment, and also it helps you prepare for the actual midterm. The other thing also, you have a quiz that is due November 11th, just a few days after the actual midterm. But since it's there are only 36 items in it, so please go ahead and take care of it. And that should also be able to prepare you for the actual exam. There is a homework 5 that is actually due again after the actual midterm. So please take care of that and make sure you do that. And in addition to that, there is a discussion that is due just a few days after the actual exam. And this discussion in here is due this weekend from this week. So next week, basically, in terms of assignments, you should not really have a lot of assignments due before the actual midterm. And that is because the focus is the actual midterm. We need to focus on it and make sure that we do well in it, okay? If you do the entire review, and you just submit basically just to sort of look at it, and then you submit and you get, let's say, for example, 20% in it, about 25, 30%, 30 points, basically. And yes, you're going to get the full credit. You're going to get 113 points, but that may not be enough. In other words, you really have to go back and make sure you score the highest possible in the review to actually do well in the exam. The hope is that you score 100% in it, of course. Now, what happened? Let's say, for example, the first attempt you scored 80%, okay, or 25%, or even 1% of the actual exam, actual review, I'm sorry. Then you're going to get a full mark for it. You get 113 points. So now you should not be hesitant to take it again, because no matter what you score later on, it's still going to give you the full credit for it. It's going to score the highest. In which case, it's going to be the perfect. The point I'm trying to say in here is this is a useful tool to help you prepare for the exam and in the same time get credit for participation. So take advantage of it, okay? On Wednesday, we're going to discuss the homework, basically, and how to handle it. And you have a quiz, which is actually a timed assignment. So please make sure you review all of the content before going to it. And these, of course, are the units in here. And there is a discussion item in here, or as always, every week in here that we've been doing. So this is a graded assignment also. And this is basic, and that goes also toward your participation, of course, the fact that you're engaging in class and doing what you need to do to pass the class. So this is in terms of this week. So let me get into the content. So let me go back and try to find the file that we're supposed to go through. We are in, no, not so. So we're supposed to go to unit 48. And let me open unit 49 also, because we're going to need it too. So obviously the other two units, namely the one dealing with electricity, with light, we're going to leave them for Wednesday, okay? Okay, so let me share with you the screen. I don't know what I was sharing. I was actually the class. So let me share with you the screen, and that is unit 48. So what unit 48 and 49 are dealing with are two last remnants, basically, of the solar system. And then we're going to jump to light. We're going to jump to light. We're going to move back to the units 21, 22, and so on and so forth, dealing with light, because the ultimate goal is we're going to move from the solar system and start exploring the stars. So this is basically how the plan is. And you will discover that light is actually the best mean, if not the only mean, to study stars, because they're too far away to send probes or anything like that to study. So before doing that, we need to finish, first of all, the solar system. So we have two topics, namely the ice worlds. And what we mean by it basically are both the moons in the outer planets region, basically past the frost line, past the imaginary line that is between Jupiter and Mars, and that line where water freezes and becomes a solid in all the forms, unless it's protected by thick layer, like, for example, for the case of Europa. then that is the ice world. So the moons of, for example, Jupiter, Saturn, and the other planets, and also the dwarf planets, okay? So we're going to talk about their properties, we're going to talk about their geological properties, and the liquid water underneath, and the TNOs in general. What I mean by TNO is trans-neptunian objects, okay? Objects that are past Neptune. And then we're going to discuss also the comets. Comets are objects that come from the outer regions of the solar system, namely two main regions, a Kuiper belt and also an Oort cloud. And we will discuss the difference between the Kuiper belt, which is basically the biggest difference is it's too close from the sun. It's relatively about 50 astronomical units, so it's not too far really. And the Kuiper belt is in the same plane as all of the planets that orbit the sun. So it's in the ecliptic plane, and it's basically in the thermal, it's flat really, more or less. And then you have the Oort cloud, which is more of a spherical shape, a symmetrical shape that goes around the sun, and it's too far. It extends hundreds of thousands, basically several thousand astronomical units from the sun. And because of its distance from the sun, its properties are a little bit different in terms of its distribution of its components. So those are the objects that come to us from those regions are called comets. Obviously, the objects that come from the Kuiper belt, or even closer, they have a short period in a sense. Their semi-major axis is small versus those that come from very far away. So their period in this case is extremely large. Okay. So those are the objects that we're going to be discussing in the solar system and discuss their properties. And then in the second part, we're going to be dealing with light. Okay. So again, as I mentioned before, and we discussed this part of our study actually for the satellites of the satellites in the solar system. And for comparison's sake, in here we still have the moon. And we have, of course, the big objects in the solar system. Those are basically, for the most part, the icy object, with the exception in here for the case of Io, which is really has a lot of sulfur and silicate in its structure because of its proximity from Jupiter. Is undergoing a lot of geological activity. Then, of course, you have Ganymede, which is for the most part is an icy structure. If you look at the surface, you will see it's marked with some basically deformations, but for the most part, it's an ice, which is a super thick ice, and underneath that there is liquid water. Ganymede is the next one. It's the biggest moon in the solar system, and it's actually bigger than Jupiter. I'm sorry. Bigger than Jupiter. Nothing is bigger than Jupiter in the solar system other than the sun. Bigger than Mercury, that's Ganymede. And then you have Titan, which is the other object in here that is of interest actually to us in here in terms of explorations. And we have actually Callisto. Callisto is slightly of the same size, slightly less than Mercury, but that's actually the third object in the solar system. In terms of composition, we're going to explore these objects. Then comes the smaller objects. There are significant distinction between these objects in here and the smaller ones. So the Earth's moon sits after Ganymede, Titan, Callisto, Io, then the Earth's moon, then Europa in terms of size. Then you have the smaller moons, okay, or smaller objects in this case, because you have a bunch of dwarf planets. And actually, moon Charon is the moon of Pluto, and then you have Triton, which is the moon of Neptune. Triton is bigger and similar in structure to Pluto, actually, which suggests because of its orbit that is irregular around planet Neptune, that it is actually a captured dwarf planet. So if Triton was orbiting the sun, it would be the biggest dwarf planet, bigger than Pluto. Eris actually is slightly bigger than Pluto, and that's the one that caused the whole mess for Pluto in terms of demoting it and making it into a dwarf planet. Because when you have objects that start to pop up day in, day out, it makes learning about the planets was a little bit of a challenge, because if we kept Pluto, we must keep Eris, and then of course, Triton is not possible in this case because it's orbiting Neptune, so it's a moon, it's a satellite, but regardless of its origin, of course. Then you have Haumea, Quaoar, Makemake, Sedna, and then Orcus. Obviously, Charon in this case is a moon of Pluto. There are two versions of it. If you look for it, there are people who call it Charon, and there are people who call it Charon. And I think the discoverer named it initially after his, really, he tried to include his wife's name in it. Okay. So the point being in here is this is a moon, so it's not going to count in here, but the others are also dwarf planets. And actually, there are more in this, okay? These are not all of the dwarf planets out there. So this is just a sample of them. But of course, the biggest ones are these ones that I'm showing in here. And the picture of Sedna or even Makemake and all of these ones are a little bit, kind of renditions. They're have not been seen. I mean, we don't have any real pictures of them, but they're simulations of what they look like based on the models that we have, based on their orbits, based on their shape, based on their mass, based on all of the other properties. The peculiar part in here, of course, is Haumea. If you look at it, it's not anywhere spherical. It's more of an elongated shape, okay? That is because it has a spin that is super fast. It spins so fast on its axis, it's really dizzying if you were to stand on it. So which makes it that it's almost trying to come apart because of that extreme high spin. So it's moving extremely fast on its axis. And these dwarf planets, they're all interesting, of course, and they have their own properties. We know that they have moons. For example, Pluto has 5 moons. The biggest, of course, is Charon. As a matter of fact, Charon, the moon of Pluto, is so big compared to Pluto itself that it is the number one, the biggest ratio of moon to planets, or dwarf planet in this case. The next in ratio is Earth-Moon, actually. The moon of the Earth is large, relatively speaking, if you compare it to its own planet. So the ratio, I'm not talking that the Earth-Moon is bigger than the Earth. No, the Earth is still bigger than the Moon. But if you take that value and divide it by the mass of the volume of the Earth, you're going to find a certain value. If you compare it to Charon versus Pluto, of course, Charon is smaller than Pluto, so the ratio is still less than 1, but it's the highest number there is, to a point that Pluto and Charon do not orbit Pluto itself. They orbit a point between them called the barycenter. And actually, this is true for all orbiting objects. There are no two objects that orbit, there is no two objects that orbit exactly where the other one is stationary. There is always a motion around the barycenter in the opposite direction, with the exception that if an object is solar, for example, if you take Jupiter and you take, for example, Io, the ratio is ridiculously small. That Io is a tiny fraction of Jupiter. So for all practical purposes, Io orbits Jupiter. And the same thing for all of the planets around the sun. They all orbit the sun practically. The sun is not moving, with the exception of Jupiter, because it's massive enough that it impacts the sun slightly, that the sun actually wobbles around the barycenter. So that's basically what this notion is. But it's noticeable in the case of Pluto-Charon system. There are 4 more other moons actually for Pluto. It's not the only moon that they were discovered recently. And this is basically the extent with which at least we're going to be exploring these objects in here in the solar system. Again, the Galilean system are these 4 moons. They're the moons of Jupiter. Okay, their temperature is between 100 and 130 Kelvin. So it's low. So when you see 130 Kelvin, that is low. Just to give you an insight into this number, right now, despite today being a cold day, we're sitting at around 300 Kelvin. I wore a sweater actually today with long sleeves, so because it's kind of cold a little bit. But the point being in here is that this is 300 Kelvin. Imagine if you are 130 Kelvin or 110 Kelvin. This is about 200 Kelvin less than this temperature, which is about 200 degrees Celsius less than this temperature. So if this is, let's say, for example, 20 degrees Celsius, subtract from it 200. So it's going to put it, what, 200 deducted from 200, from 300, from what is it, 20 degrees Celsius, 20 degrees Celsius. So you're going to be in negative 180 degrees Celsius. That's a very low temperature. It's going to be probably about negative 120 or negative 140 Kelvin. Sorry, Fahrenheit. Okay, so you do the math and you do the kind of conversion. The point being in here, it's extremely cold. Okay, these places are so cold. Obviously, the water freezes at 0 degrees Celsius. So 0 degrees Celsius freezes water, meaning that these temperatures are well below freezing temperature. In terms of Kelvin, the water freezes at 273 Kelvin. That's how water freezes. Obviously, 110 or even 130 or even 200 Kelvin is below freezing temperature of water. So water is frozen ice. That's why the title of this topic is Ice Worlds. And when I say ice, I don't really mean water also that freezes. Other gases also freeze at this low temperatures. So the word gas in this case refers to all of the other objects. Okay. This is Io. Io is the closest object to the solar system. Okay. I don't know why these notes are here. So this is from a previous thing. Delete them. I don't need them. So again, Ice is the closest moon to Jupiter. Okay. And it experiences, because of the proximity, it's really being granted that its path is not exactly a circular. So at some point, here is a scenario, and this is actually part of the discussion today. So you have Jupiter, let's put it in here. You have Io, put it in here. You have Europa, put it in here. Ganymede, put it in here. And Callisto, put it in here. This is not to scale by any stretch of imagination, okay? At some point, you have this scenario. So Jupiter is pulling on it. Europa is pulling on it. Ganymede is pulling on it. And Callisto is pulling on it. Granted, the most effect in this side is going to be Europa because it's closer. And obviously, Jupiter is going to be always pulling on it. So it's really a drastic thing. At some point, because it's moving super fast, it takes about 42 hours to go once around Jupiter. The others are slow. This takes about 3.5 days. This way, it takes about 17 days to go around Jupiter. So at some point, it's going to be on the other side, whereas everybody else is on this side. So you have Jupiter still, you have Io on this side, and you have the others. You have Europa, Ganymede, and Callisto. So now Europa is pulling on it. I mean, Jupiter is pulling on it. Europa is pulling on it. Ganymede is pulling on it, and so is Callisto. So they are pulling on it on one side. So now it's being worked. So at some point it's like this, some point on the other side. So it's being basically kneaded, like you take the dough, for example, and you're trying to work it out. And that creates friction, that creates heat, and that creates an extremely active moon, with volcanoes erupting all over the place in here, and that's actually magma flowing on its surface, and you have these charred regions that are from the gas, basically, that falls back on it, and that creates the most active volcanic system, object in the solar system, period, end of the story. It has this kind of yellowish color in here, and it's because of the sulfur that is actually being produced constantly. The plumes that you see in here, these are eruptions from the surface of Io. It is ridiculously an active moon. Obviously, the biggest effect on it is coming from Jupiter itself, and it's close from the moon itself. I mean, close from the planet itself. And as you get closer, I mean, relatively speaking, it's further from the Jupiter, not relatively, I mean, number-wise. Actually, it's slightly further from Jupiter than the Earth's moon is. But remember the size of Jupiter. It's about 11 times bigger than the Earth. So the actual distance is less, actually, if you were to travel between Jupiter and from to Jupiter, to the surface of Jupiter. Combine that with the tremendous mass of Jupiter, which is 300 times the mass of the Earth, then you have tremendous gravity that is pulling on it on one side. And that is causing it to go through tremendous heating, which is called tidal heating because of the tidal waves, basically. Those are tides, except now there is no liquid surface on it. To see that it's actually the actual surface itself is stretching in and out. That creates friction, and friction creates energy, and that is basically what's going on in the case of the moon. Europe, on the other hand, is further away, so it has less effect, and it's affected by, again, two objects on one side and two objects on the other, and it's sitting in the middle. Obviously, there are far more moons for Jupiter than just these four, but these are the biggest players. The others are too tiny to even have any effect whatsoever. So we know it has an icy, basically, a surface. It has cracks on its surface, as I was describing, but it's an icy surface, I mean, on this outer shell. I mean, you can just check the reflection on the surface, the reflectivity, and that is of the water. It's highly reflective, the surface of it. It probably has a metallic core, but we know it has a liquid ocean underneath its thick crust, which is really, in this case, a solid ice. Okay. How do we know that? How did we come up with a conclusion that it has a liquid ocean that is salty? It's because of the magnetic field. It has a weak magnetic field, albeit, but it's good enough to indicate the composition of the liquid that is underneath. Furthermore, there are eruptions that are coming from the surface that is of liquid water. Obviously, if it comes out, remember the temperature is between 110 and 130 Kelvin, which is way below 273 where the water freezes. Then in this case, it becomes solid. And that's what shows the features that you see in this case, okay? You see the features on its surface from those eruptions. There is a mission called the JUICE, which is going to be launched, I think, in about 2 years in cooperation between NASA and ESA. NASA stands for the National Aeronautic Space Agency, and ESA stands for the European Space Agency. They're combining for this mission, which is, I think, going to launch in 2024 or 2025. I don't exactly remember the date. But the point being in here, this is Jupiter icy moons, basically, exploration. That's what the mission is. It's going to focus mainly on Europa. The plan is to go around Europa and capture the water that is coming from the plumes, from this case in here, that is constantly basically escaping, because remember, there is heat also during the same tidal heating. And unlike the moon Io, where it's erupting actually magma, or basically fire that is coming from there. Now this is the hot water coming out, erupting. This is called cryovolcanic activity. So basically this activity now will collect the water. The mission is to go around Europa, collect this water as it comes out of Europa, and as it does, it's going to find, or at least try to find, life in the water. Because listen, this is similar conditions to the oceans underneath the surface of the Earth. They don't really require the sun for activity. So we know that extreme life exists under tremendous pressures in the surface of the Earth, in the surface of the Earth, in the oceans. and it gathers energy from the heat that is generated from the Earth. This is similar because you have a rocky structure underneath that is going to generate a lot of heat because of the tidal friction, and the water basically is similar in composition to the water in here on Earth. So, and as a matter of fact, there is more water in Europa than all of the water on the Earth. If you take all of the water on Earth, it's less than that of the water in Europa. So Europa now presents a very, very good opportunity for us to go and find life underneath its icy crust. Okay, this is the plan. There are two possibilities for this question. Either we find indeed life as we know it, like carbon-based life as we know it, or we don't. In either case, it's an interesting result. If we do find it, that is actually a big step forward trying to explore basically life in another planet and other environments other than Earth. If we don't find it, this is actually an interesting question also that we want to understand. Why in the world there is no life in there? Conditions are ripe for it. Conditions are perfect for it. There is a thick layer that protects it from any kind of radiation. And there is actually a conditions in terms of energy, ready for the cycle, the nutrients and all of the things for life. So it should really exist. So if it doesn't exist, how come Earth has life? Because it has similar conditions, and now this place has it, the other one doesn't. So it's really a good challenge. Obviously, the mission will start somewhere in the mid-30s, basically 2030, 2034, I think is when the mission is actually. Because yes, they're going to launch it, but it's going to take a long time before they arrive there, because it's far away. Remember, it's about 5 astronomical units from the sun. So, and we're only 1 astronomical unit from the sun. So this is a very, very far away moon. And by the time they reach it, they have to really get ready themselves to start orbiting. So you have to really get the mission going before you start collecting data. So again, the plan is to go and try to collect samples from that. They're asking what happened to Io. Well, Io, at this point, it's too hot for it, for conditions of at least similar life on Earth to exist. Okay. Besides, the material that is being, Io is losing a lot of its mass on a regular basis because of these volcanic activities, and because of its proximity from Saturn, from Jupiter. Jupiter has tremendous magnetic field. It's taking those charged particles and dumping them on the north pole of Jupiter and the south pole of Jupiter, creating creating basically the aurora similar to what happened on Earth, except that they are happening on Jupiter, due mainly to Io. But again, the mission to Europa is a really promising mission, and I look forward to it. Hopefully, I will be around at that time to see it. That's really something that's going to advance science big time, because either we find life, which is really good. That's what we hope to do. Or we don't find life, and that is actually an interesting also discovery by itself. Okay, this is not the only mission though. We still have another mission. So the other two moons in here, they're Ganymede and Callisto. Ganymede and Callisto, they're a little bit far away from Jupiter, really, to have similar promises. Actually, maybe Ganymede is a potential also similar to Europa. But Callisto, in terms of surface, is actually a little bit more uniform. Ganymede and Europa are highly basically differentiated, meaning that the lighter materials stay up and the denser materials go down. So that's in terms of density. But Callisto and of course, the moon Io is really going through a lot of activity as we're talking about it right now. But Callisto is less differentiated, and its surface is actually highly impacted. Even the surface of Ganymede too. meaning that they are ancient surface, because those impacts from the early bombardment stage from the solar system are still there. And it doesn't look too different, actually, if you look at it and try to compare it, for example, from the Earth's moon or that of Mercury. So you see the impacts from the early craters, they're still there. From the early impacts, they're there. So the craters are on the surface, and you can deduct that they really did not go through a lot of geological activities, especially the case of Callisto, which is the furthest of the four moons of Jupiter. And it has also all kinds of dust also on its surface. So that's basically what this structure is. Now comes Titan. That's the other mission also for what is 300 Kelvin? Oh, that's room temperature. That's today. Yeah, that's room temperature. It's always 300 Kelvin. So again, Saturn is the second moon of in the solar system, second satellite in the solar system. This is the only object outside of the Earth's moon, Mars, and even Mars and Venus. This is the only object in the outer solar system where we actually successfully landed an object in there, maybe Huygens, okay? It landed on its surface and it gave us a picture of it. Now, its surface temperature is even colder than that of the moons of Jupiter. So if you thought that the others were cold, this one is even colder, okay? So this one is about negative 150, probably negative 170 degrees Celsius. So it's extremely cold, okay? So you would not be able to survive on it. You're going to freeze to death. Any object in there. So no living organism, at least from the ones that we know on Earth, could survive the surface of the moon because of the temperature. However, the pressure on its surface is ideal. This is slightly higher than the pressure on the surface of the Earth. And that's why it looks hazy. It looks actually like a from a distance, it looks like a Venus. And this is an interesting moon by itself because of the fact that its structure from inside has a lot of promises. It has a cycle, a liquid cycle on its surface. It's not water. It's mainly methane, and that's something that we're going to explore again in another mission. Forget the name for it, but it's also launching again cooperation between, I think also, I'm not sure if the Canadian agency is involved or not, but NASA and ESA are also involved in it. And on its surface, there is a liquid ethane in this case. So again, this kind of things are based on the models. When the first mission of Huygens was launched there, we were not sure if the surface, because when we looked at it with telescopes at that time, we saw the surface, the hazy surface. So the belief was maybe there is an ocean of methane and ethane and all of these carbohydrates basically on its surface. So the shape of Huygens was so that when it lands, it floats, or at least that's the hope, and it's on the liquid surface. But then it found solid surface on its ground, not the surface that you might have in mind, not the surface that we have outside in here. It's mainly ice water because it's really, the rocks are made out of ice water. So there is a solid surface, but also liquid regions of it. So there is all kinds of conditions because of the cycle, the liquid cycle, the atmosphere, the pressure, the source of energy. It's not too far from Saturn also. There is actually a potential for life, and it should exist also, but not necessarily a carbon-based life. It needs to convert the other gases, basically breathes methane, which is really in the atmosphere, and nitrogen, which is the main component of the atmosphere of that planet, and uses it for whatever other processes, not basically based on oxygen the way that we know. So this is potentially, and it should have a different form of life. Again, the mission is trying to explore it. Same thing. If life does not turn out to exist in this planet, so the question, this moon, I should say, question is why not? course, all of the conditions in terms of energy transformations, in terms of the suitable conditions, especially with the water cycle on the surface and the not water, I meant liquid cycle on the surface, then this is actually something that is of interest to us if it doesn't exist on that moon. The surface is highly evolved actually in the past. It's similar to the surface of the Earth because of the geology on its surface, because of the weathering on its surface, because of the atmosphere on its surface, and because of the cycle of the liquid on its surface. So the surface is changing, except that, just like the Earth, there are some ancient impacts that are actually remnants of that. For example, the Earth has a lot of impacts also on its surface. A shape, for example, on the Yucatan in Mexico is an indication of there was a big impact about 65 million years ago, coinciding with the extinction of the dinosaurs. There are other impacts of Arizona meteor crater is an example, but they're all over the world, so it's not just in these places. So this is a remnant of the early impacts, but those are the large ones. Again, if an impact hits a moon like this one with a thick atmosphere, and if it's a small meteorite, for the most part, it's going to be pulverized in the atmosphere before it reaches the ground. It has to be big enough to create a mark in here and stay on the surface for a long time. Obviously, it's not going to stay forever because of the fact that you have these cycles on the surface. Again, this is the pictures that Huygens sent us. Okay, and this is the surface of the moon. So it's really an interesting surface in here. As it was landing, it was sending the data. And of course, because of the extreme low temperatures and the lack of solar panels to actually, it landed only with batteries using basically radioactivity. So at the end, when the energy ran out, because even if you have solar panels on the surface of the moon, the thick atmosphere of the moon will prevent from collecting a lot of light. Besides the fact that the moon is far away from the sun. Remember, it's 5 astronomical units, and according to the square law, the intensity of the radiation of the sun drops one over the square of the distance. So if it's on the Earth, it's one amount. On the moon itself is going to be 1 over the square of 5, which is 25. So 1/25 of the energy will be dropping there anyway. Besides, the thick atmosphere is going to absorb most of it, so you're going to hardly have any radiation on the moon to use. But you're going to have some if you have big enough panels, basically solar panels. Okay, we talked about Neptune's moon Triton, which is the next object. Again, we think that in terms of structure, it's similar to that of all of the other moons, because it must have formed from some smaller, basically, objects. But then Triton is larger than Pluto, and is almost as big as Europa. So it's really an object that actually the surface looks awfully similar to Pluto, and again, Triton itself is not really a native moon of Neptune, but it's a captured moon. Okay, there are no planned missions, at least that I know of, for Neptune. Then you have Pluto. Pluto, with the New Horizon that flew by in 2015, around 50,000 miles per hour, basically, around. Reached about a few hundred kilometers from the surface, give us these beautiful pictures in here, and discovered, of course, the methane, nitrogen, carbon monoxide, and water on its surface. Water is not in the liquid form and still in the ice form. All of these are actually ices. There are darker regions, obviously, and cratered surface. There are surface that seems to be active, and there is the heart of Pluto. You have had a chance to look at it. There's a shape of heart in here that forms from some sort of an impact in the past. Surface temperature on Pluto is ridiculously cold, and Pluto goes through a cycle where it goes closer to the sun. It has a more eccentric path around the sun than most of the other planets, actually. And because of that, it gets closer at times from the sun, in which case some of this methane and nitrogen especially starts to evaporate basically and form a gas, forming an atmosphere. But then when it gets further away, it's going to again solidify and basically freeze. So when it evaporates, it actually goes through sublimation process, in a sense, from solid ice to straight gas without going through the liquid stage. Okay. So this is an interesting object by itself, and it really, when it was discovered, it held a lot of promises. People thought that this is actually the 9th planet, and it held the title for a long, long time. It held this title as a planet for a long, long time. Then something happened. Eris was discovered, and other dwarf planets were discovered. So at that point, it started to create debate, and the Astronomical Society decided to create a new classification called dwarf planets, and Pluto was put one of them because, among other things, Eris is bigger than it. If you're going to classify it as a planet, so Eris will be another planet, and then why not the others? So there was a debate about it, and that's where its status stands right now. I mentioned its moons, and there is Charon in here. Charon and Pluto are relatively big, but there are other moons that were discovered in 2005, 2006, and then more recently, 2011, 2012, Kerberos, Styx, and then Nix and Hydra are the other moons. So it's really a system by itself. The fact that it's a dwarf planet does not diminish this one in here whatsoever. As a matter of fact, there are studies right now that suggest maybe there is a different kind of life form on its surface that's taking advantage of that basically changes in its composition in the atmosphere. As a matter of fact, a lot of this material that has this reddish color is actually carbon-based materials. So it's really some sort of organic matter, although its origin is not necessarily life, but from organic chemistry. It's still an interesting system by itself, and it has a lot of moons actually that were discovered. The story of its discovery itself is a really great story also on how it was discovered itself. Anyway, Pluto's orbit, as I was saying, it's a little bit eccentric. If you look at it from the top, it looks like Pluto crosses paths with Neptune, but it doesn't really, because it's not on the same plane to begin with. It's in and off the plane of Neptune, but it gets very close at points and very far away at other points from the path of Neptune. And this is how we think also what happened to Triton. Triton had a similar path, but it ventured too close from Neptune, and Neptune captured it. Pluto and other objects that are past Neptune all have this bearing name now of TNOs, okay? Trans-neptunian objects. The TNO stands for any object that passed Neptune, and they form this kind of whizzing thing that you look at when you look at them going around. This is not the entire picture, though. There are far more objects in here than what is represented in this image. Note the following. You have, of course, Pluto on one side and Orcus on the other side. Orcus and Pluto, they are always opposite to one another. Then you have Quaoar, Haumea, Makemake, and you have Eris. Eris is this completely off of the chart in terms of its path going around the sun, and in terms of the ecliptic is here in the picture with the blue path of Neptune, and anything outside of that are called TNOs. Sedna is an interesting dwarf planet in a sense that right now it's relatively speaking closer from the sun than which could be, because its path really takes very, very far away from the sun. That's why it was discovered. This suggests what is out there. One of the things that is being discussed now heavily is why all of these paths seem to be converging at some point. When an object apparently is in here, they all move to this side, and when this object right now, what we know it in here, so all of these objects seem to be influenced by another object that seemed to be another planet, according to the calculations, bigger than the Earth, and its orbit is very, very eccentric. Could this be, there are several theories leading to it, First of all, it's in a region of the sky that is very far away from the sun. Remember, Neptune's orbit is this very tiny orbit in here that you can. And Neptune is not close from the sun either. Remember, it's about 30 astronomical units from the sun. So it's 30 times far away from the sun than the Earth is from the sun. So it's very far away, and this planet in here dwarfs that path. So it's very far away. So even the slightest changes in its path is actually a lot of changes in actual, slight angular displacement is a lot of change in the actual path, and gives you very wide region to look for in the sky. It couldn't be discovered today because we're having difficulty. So this entire region are probable regions where you can find it. And this is a huge region of the sky. Just to compare it, this is much, much, much bigger than the path of Neptune. Neptune was discovered also with math, by the way. When Uranus was discovered, Uranus, basically the assumption is that, okay, it's orbiting the sun, so it's influenced by all of the other planets and the sun. But there was a change in its path. There was a problem with its path. So two independent astronomers made calculations and predicted there must be another planet out there that you go and look for it. And sure enough, Neptune was discovered. This is exactly similar to that. What happened with the Neptune is happening actually with the so-called the ninth planet. So the ninth planet was discovered by monitoring all of these objects in here and discovering there must be another planet much bigger than the Earth is in this more or less region of the sky, which is kind of hard to really honestly find at this point because of its big region. Besides the fact that this planet is not really emitting light, it's reflecting light, it's just too far away to reflect, to receive much light to reflect. So especially if its surface is not icy surface, it's probably absorbing a lot of light. So you're not going to find, you're looking for an object that is too dark, okay, and very far away from it. Which brings to another hypothesis for Planet 9. It could be a primordial black hole to begin with masses that is similar conditions, but size that is extremely small. But it doesn't emit light, so you're not going to see it, even if it's close by, okay? You have to do other techniques called the microlensing or other techniques to really find it. So there is another hypothesis that Planet 9 actually is not a planet altogether. It's actually a black hole, although this black hole is so tiny to be really a big concern for anything because it must be evolving in this path in here. So there is a hypothesis for that. Yet there is another hypothesis that maybe these paths are not really suggesting the existence of an object altogether. So there is all kinds of debate right now, but this is the hunt for Planet 9 right now is ongoing in science because of the fact that you have this oddity in the paths of the other objects. Okay, again, we discussed Planet 9. This is its processes. Okay, this is a summary of all of the this object that we saw. Pluto has a diameter of 2,300 kilometers. Eris is slightly bigger. Pluto has a mass of 1.3 times 10 to the power 22 kilograms. Yes, Eris is slightly bigger. So Eris is bigger both in size and also in mass. Okay. Its orbit is about 40 astronomical units. It's very far away from the Earth. From the sun and the Earth, it doesn't matter. The Earth is at best 38.4 astronomical units. Now Eris is much, much further away. It's almost twice as far away. The eccentricity of Eris is even higher, meaning that it gets closer to the sun at some point and further away, relatively speaking, of course. Okay, Sedna by far, and that's the one I mentioned in here, it's even higher. It's almost 1. Okay, its size around 1,500 kilometers. Its mass is still unknown, and so is Makemake, by the way, which are similar in size. But this one is relatively close by compared to this one, which at some point will be very far away. Okay, Makemake is slightly more less eccentric, I should say, even than that of Pluto. Haumea is similar in proximity, in eccentricity, and its path is also, this is a semi-major axis, so it's really less eccentric, and it's slightly anywhere between almost 1,000. What is this in here? This is not multiplied. This is wrong. Okay, Haumea is between 900, 1900, so almost 1900 kilometers to 2,000 kilometers. This is not correct. Okay, because I'm sorry. I gave you the wrong impression here. So it's correct. It's correct. So this is what is meant. On this side, it's 1900 kilometers, and in this side, it's only 1,000 kilometers. So it gave it this shape in here. Okay, so it's 1900 around the equator, and only 1,000 around the north to south pole. Because remember, it's spinning super fast. That's Haumea. Charon is similar to, 1,200 kilometers in diameter divided by 2,300 kilometers. That's slightly about 1/2, basically. It's a big moon. And it's a satellite, so we don't talk about its eccentricity, because its eccentricity follows that of Pluto. This is Quaoar. Quaoar has 1,000 kilometers, and it's a highly less eccentric. Basically, it's circular path going around the moon. Now, this is the object of focus in here at this point is Orcus. Orcus is only 950 kilometers, so it's a very small dwarf planet. And its eccentricity is similar to that of Pluto. And its size, of course, is less because of the fact its size is less, but its mass also is less. But look at how far is it from the sun. It's identical number as that of Pluto, meaning that they are actually in resonance. One of them is on one way, the other one is the other way, and they're always continuously moving in this path around the sun. So they are actually on the same path, except that they are not sitting at the same point. So they are always orbiting the sun in opposite directions. Okay, that's what that is. With the eccentricity very close from each other. And also remember, eccentricity is not a fixed number, it changes over time, but that's not a big deal. But the big deal in here is the semi-major axis, the same number. So they are the same distance. They are not next to one another, they are opposite to one another from the sun. Okay. So this is this unit. So how we're doing on time, still have some time. Let me share another unit, the unit 49, and we're going to talk briefly about unit 49. So unit 49, as I said before, deals with the comets. Comets is a phenomenon that was known in the old days, basically stars that appear for a few days, few weeks, and then disappear. And then turns out that comets are actually another interesting objects, and by far they are one of the most interesting objects in the solar system. They are the ones that bring water and other minerals to planets. But water is their main load. They come from a region where water formed to begin with. Remember, hydrogen and oxygen, they were expelled from when the solar system formed there, according to the nebula theory, and they froze far away past the frost line. So the Earth, when it formed, whatever water it had, because of its extreme high temperature, was broken down into hydrogen and oxygen. For the most part, the hydrogen basically left because it's lighter material, and the oxygen combined with the other elements in here, and carbon to form carbon dioxide, and other metals to form all kinds of dioxides, and the silicates on the surface, and so on and so forth. So water was devoid of water. So was all of the other planets. So was most of the other moons. Now comes the place where the water actually froze and formed this solid objects and impact. During the impact, that released a lot of water on the surface of the Earth and all the other moons. So comets are really the messengers that put all kinds of resources to the planets, including the Earth in here. So again, where they came from was really a big debate in here, because their origins was a mystery until basically Mr. Oort basically came up with this assumption that first of all, they must be coming from far away, but they're bound to the sun. And this region that they come from, they can be calculated, and that's really how the Oort cloud was discovered. Now it's actually more and more objects are being discovered in it. So a comet really is, it has a nucleus, of course. That's an icy nucleus. As it gets closer from the sun, it heats up, and those ices starts to evaporate. So a coma will form around it that extend about between 60, about 100,000 kilometers. And then outside of the coma, then you have another region that is a hydrogen envelope that forms around it. Remember, hydrogen is lighter than the lightest element out there, period, end of the story. And that is how it looks like. So you have a hydrogen in here, and then you have the coma that forms, and the coma starts to extend and forms a tail. There are two kinds of tails. There are dust particles that are going to form straight out, basically, by the fact of inertia, and they're going to start to bend because of the, like a projectile, basically, when you throw it. However, there is a charged ionized version of it, basically, that loses electrons, and that ionized charge will be repelled by the magnetic field of the sun, and that is forming a straight line. So this is in a nutshell what the structure of the comet is. So inside you have a nucleus, you have a coma that forms, you have a hydrogen shell, and then on top of that you have the or hydrogen envelope, I should say, and then you have on top of that the tail that forms two forms. There is a neutral one, a dust particle one, and then you have the ionized version of it. You have to remember that dust is not really carried with the comet anymore. It's going to be left behind it. So as the comet is moving, the dust is going to drag behind and stays behind forever. And the comet starts to lose more and more material as it goes around the sun. And every time it passes by, obviously, if it's 5 astronomical units or further, on the other side, it's still solid, so it's not losing material. But as it gets closer, as it passes Jupiter, about 4 astronomical units starts to evaporate, and it starts to lose materials. The Earth is 1 astronomical unit, so by the time it goes around the sun, it loses a lot of material, then freezes back around 4 astronomical units and goes to wherever it came from until it makes the next passage. So in doing so, it loses materials around the time. So that's why where the calculations were. So if I were to start with a big object, the icy object, how long will it take for it to dissipate and disappear completely? If it is a nearby object, then ultimately this time is less. You will not see that. But if the distance it comes from far away, those objects, they must be coming from then one of two regions, either the Kuiper belt, and those are short-lived, relatively speaking, versus the one that come from these faraway regions that take a long time. So that is basically where the calculations were. Furthermore, as the Earth is going around the sun, it's going to encounter the dust that is left by these comets. And that is what shows as meteor showers that basically you see on specific amount of time, because as the Earth goes through those, they will enter the atmosphere because of the Earth is going around them and basically burn and give you those meteorites that you see in the night skies during certain amounts of time of the year. So this is in a nutshell the story of this whole unit. Okay. Again, you have some famous comets. The biggest one of them, of course, is Halley's Comet. This was discovered in immediately after Mr. Newton explained the law of Kepler's laws. So when Halley looked at this object that is bright in the sky, and based on its displacement in the night sky, basically the angular displacement, he was able to predict its velocity, and based on its velocity, he was able to determine basically how far it is and how all kinds of other properties. And the biggest thing in here is he predicted when it's going to come back next time around. He said within 76 years and a few days, it's going to be back. And sure enough, it reappeared within a few days from his calculations. So that's why it bears his name. And that's a confirmation, triumph for Newton's laws of universal gravity. So it really is an interesting object. We were able to basically send probes to these comets recently. The DART mission that really went to an asteroid, and basically that's an asteroid, not a comet, really. Basically make an explosion on it, trying to prevent, because these things, they could also be deadly. So comets are not something that is because when they fall, they bring a lot of energy with them too, and they could really cause all kinds of changes to the planet. And this is what we think happened to Venus. As a matter of fact, Venus was more hospitable to life than what it is today, but something probably triggered those volcanoes, and most likely is an asteroid that fell on it that really caused all kinds of problems on the planet. So again, the dust tail starts to form when it reaches a certain point from the path, but that's not the only form that you have. So you have the dust tail that follows basically the trajectory like this. Then you have the ion tail that forms, and that is due from the magnetic field, basically, of the sun pushing this radiation in different ones, because it's charged. So that's what an ion is. So again, when the nucleus is far away at this point in here, it's still solid ice. Then when it starts to get closer, within about 4 astronomical units, then it starts to warm and it starts to evaporate. And as it evaporates, it forms the coma now, starts to form. As it gets closer, of course, that becomes more and more intense because the heat increases. And now there are 2 distinct tails, and they're pointing always away from the sun, okay? The first one is due to the inertia, namely the dust tail. It's like, for example, you're sitting in your car and somebody accelerates, so your body tends to move back. So that's really the effect of that motion. So it's really the dust that is left behind it. And then there is the other one, the ionized version of it, and that is actually going to be reflected by the magnetic field. And both of them are pointing away from the sun. So whichever way the sun is, they're going to point away from it. But the first one is due to motion only, okay? And the second one is actually due to the magnetic field of the sun and charged particles, because the charged particles, I mean, when I say magnetic, it's a charged particle. The radiation from the sun is actually charged, and you have charge against charges, so they are repelling each other. So as you go closer, again, the tail always changes direction, and it changes direction. And again, this one is still following the inertia, actually. And this one also is still now, not really, it's the pressure, I should say, not the inertia. There are 2 phenomena associated with radiation. I should really correct myself quickly here. So there is the pressure due to the radiation pressure. And this is the one that causes the dust to point away, okay? In addition to that, there are the charged particles. And the charged particles from the radiation, from the sun, solar charged particles. These are the coming from the sun. So this, they cause the ion tail to point away. I'm glad I caught myself before. This one really. So these are the 2 causes for the tails and why they point in those directions, okay? So, but again, the dust is going to stay in here. And as the Earth goes around, it's going to encounter them. And when it does, that's going to create the meteorites. Obviously, it's not true for the Earth. It's true for all the other planets. When they go through the dust, they create all of this showers on them. Anyway, then it's going to move away. As it moves away, the temperature becomes less and less and less. As the temperature becomes less, the material starts to solidify again, and then it becomes a solid. It lost so much material in the first process in here, and it's going to lose it again next time and next time until it runs out of basically materials at the end. Okay, so the composition is mainly water, and then other carbon dioxide and all of the other carbon-based materials, basically. Okay. So again, these are the origins, and this is the hypothesis of the Oort cloud. And now, because of the fact that we actually have these comets and other objects actually now that have been discovered, and because of Voyager right now actually is inside of this region, so we are getting all kinds of information that this is actually a good, correct hypothesis. There are other objects that came to Earth that seem to be impossible to be from, or not the Earth, came around the Earth, close by the Earth. Oumuamua was in 2017, I think October 2017, when it was discovered, but it was moving too fast for it to be even from the Oort cloud. So this is an interstellar object. This is actually an object that came from another star. And its shape is kind of weird, honestly, because it looks like it's an elongated shape. Some people speculate that, actually some scientists did actually, and do still, that this is actually not a, yes, it's an extra out of this world, basically, not from this solar system at all, it came from outside, but it looks more like a suspicious object, to be more like a capsule, more like an alien artifact, more like a civilization, basically trying to, that have master probably traveled between stars and now just went by, zoomed by our star, and continuingly in there. So now probably not living organisms in it, no aliens actually, and it's probably just a robot-based maybe device. So that's a hypothesis for it. But there are some contests to this one, and the debate is ongoing right now. So still, so this is an object that was moving too fast, but most of the others there actually of this one. There was actually another one that was discovered, but the other one for sure was not an alien artifact. That was actually a year later. So now we are actually exploring objects that are coming from outside of the solar system. Anyway, again, the meteor showers that we see there, it's like when you're driving in the snow. I know we live in Southern California, we don't have a lot of snow unless you live in the mountains. But when the snow is falling and you drive your car through it, the faster you drive, the more the snow appears not to falling straight down, but appears to be coming to the windshield. This is exactly what's going on with the meteor showers in here. We are going through those dust that is left by these meteorites. So as we are traveling, we're traveling with extreme high speed, much faster than what your car speed can go. We're doing 30 kilometers per second with tremendous speed as we go around the sun. So this meteors appear to be coming straight to us in here from what the constellation is behind it. So if it looks like it's coming from Perseus, we call it Perseids. If it's coming from Leo, we call it Leonids, and so on and so forth. So that's basically how we adapt them. And usually this is an event that happens on a regular basis. The next dust that is, we just basically missed one on November 17th, those are the Leonids. And then we have some more coming, the Geminids, and those are going to be 40 to 90 meteor per hour. Okay. Sorry, yes, 40 to 90, and they appear to be coming from Gemini. So if you go out, look for the Gemini constellation. Once you find it, then hang around and you're going to see a lot of them, anywhere between 40 to 90 meteor per hour. This is mid-December. Then December 22nd, so the ones that are coming from Ursa Minor, and this are going to be slightly less rate, about 10 to 15. Okay. So this is an interesting thing, and that's really something that hopefully you guys will enjoy and explore mid-December and toward the end of December, at least this year. And then you have January and so on and so forth, okay? Well, this is in a nutshell, this unit. Remember, we have the review for the exam that is actually on campus. So hopefully you guys will go and do that. We still have 2 more units that are part of this midterm, so we still are not ready for the midterm. The midterm actually is not next week, but the week after. So it's on November 8th, November 9th, November 8th, when the review will close, okay? Don't forget you have your lunar observations. The next one is tomorrow. And if you have any questions, please let me know. Thank you. I'm going to stop the recording now.